Hi everybody. So far we have discussed about what is a deadlock and what are the deadlock conditions are there. What do you mean by resource allocation graph and deadlock prevention mechanism. Now in this presentation we will discuss about what are the mechanisms which is related to avoid the deadlock. That is, we allowed the system into the deadlock and how we are going to avoid this. This we are going to discuss in this presentation. How in what way, in a basic way, how the deadlock can be avoided. The deadlock is avoided in any system. For this we need some additional information, that is, a operating system supposed to provide some additional information with respect to the process and as well as also the resources. That is, it means these many number of resources are needed for the successful completion of the particular process. Those additional informations we need to get it from the particular operating system. Now this is a very essential information to make the system into normal state, to make the system into the safe state or the normal state. Okay, now but it is a very difficult information which which operating system suggest all the users. These are the resources are required for the process for the successful completion of its execution. That is, it have to keep in mind of its future things also. Okay, so it have to define the resources. Next, decide for each request whether or not the process should wait. That is, for every request we have to define well in advance. The operating system has to decide well in advance whether the process, if any request is raised by the process, whether it will falls in the waiting state or whether it will be executed. Okay, and also it decide whether we can satisfy the request immediately or it must be delayed. So these are the various basic informations we have to get it from the operating system. The system must consider the resources currently available. Yes, exactly. Then only we can able to know whether the process supposed to be wait or it must be delayed. Okay, the next is the resources currently allocated to the each process. What is the status of the currently available resources and the future requests and releases of each process. If a system does not employ either a deadlock prevention or a deadlock avoidance algorithm, obviously it fall in the category of deadlock only. That is, if any system it doesn't have the concept of a deadlock prevention and it doesn't have the concept of a deadlock avoidance, obviously that too many number of resources are trying to access the same resources, it leads to the concept of a deadlock situations only. So in this environment, the system can provide an algorithm, that is, to overcome the particular deadlock. The operating system will provide an algorithm, that is, first it will identify what is the state of the system and to determine for what is the purpose. I want to know the state of the system to determine whether the deadlock has occurred or not. Next, if deadlock is occurred, a algorithm is supplied. The algorithm is started to recover from the deadlock. If a system neither ensures that a deadlock will never occur nor provides a maximum for deadlock detection and recovery, then we may arrive at the situation where the system is in the deadlock state. If there is no deadlock, it is not defining any system, it is not defining whether the particular process is there in a deadlock or not, or otherwise it doesn't have the mechanism of detection or recovery. Obviously the system supposed to be in the deadlock state only, but it is very tedious for us to recognize that state. The undetected deadlock will result in the performance degradation of the system. Yes, obviously. What is the purpose of the operating system? The operating system, it has to maximize the CPU utilization. Exactly right. But if any processes are falls in the deadlock state, it means that it is indefinitely blocking. That is, the process CPU time is also kept as ideal and the process is also ideal. So in that case, obviously the system performance will reduce. Okay. So deadlock avoidance allows three necessary conditions but makes judicious choices to ensure that the deadlock point is never reached. That is, we have to carefully monitor those three conditions to overcome the deadlock. Deadlock avoidance allows more concurrency than prevention. That is, parallel execution is more than important than the prevention. Okay, when the deadlock is made, we have to make the decision in such a way that whether the current resource allocation request will be granted. If it is granted, whether it leads to the deadlock or not, that decision the operating system is supposed to take. Once again I will repeat it, the operating system supposed to take a decision if any process is making a request right now, if we are granting the particular resource, whether it leads to the deadlock or not, we have to keep in mind. So deadlock avoidance requires the knowledge of future process resource requests. That's why I said well in advance it has to define these many number of resources are requested. Okay, then two approaches to deadlock avoidance. One, do not start a process if it demands might leads to deadlock. Okay, and next one, do not grant an incremental resource request to a process if this allocation might lead to deadlock. Now this is a data success where we have R is called as a set of resources and the available, so the available resources and claim. If these claim and allocation are the two matrices, and R and V are the two vectors, where with the help of the claim we can identify what is the requirement of the particular process. For every row is dedicated to the one process. Now this is for process 1 and this is for the process 2 and this is for the process n, whereas in a column that is respective to the particular resource. This is for the resource 1, resource 2, resource 3 and resource m. And allocation. Now from this A matrix we can identify what are all the resources are already allocated, what is the current allocation status of the particular process with respect to the resource. Okay, so in detail of that particular matrix. So when we have this concept like this, the following relationship supposed to be hold. Okay, RA, what is called as R is called as a resource. Okay, so the RJ is equal to, that is J is called as a resource, RJ is equal to VJ. What is a VJ? VJ is called as the available resources. Okay, plus summation of I equal to 1 to n Aij. What is A? A is a matrix where it defines the allocated matrix. That is, the total number of resources is equal to the available number of resources plus it is already allocated resources. Okay, and C of Ij is less than or equal to Rj. What is C of Ij? C of Ij is called as a, C is meant for a claim. What I am going to claim is obviously it should be less than the particular available resources. Okay, then A of Ij, what is a A? A is meant for already allocated. So A of Ij is less than or equal to C of Ij. That is, what I have claimed, it's supposed to be the allocated is less than or equal to what I have claimed, less than or equal to what I have claimed. Assume that for my execution, if I claimed 5 resources, the operating system may allocate, I am not sure about, the operating system may allocate all the 5 resources at a single time or the less than that. So that is a condition of, that is a relationship of the serial number 3. With these quantities defined, we can define a deadlock avoidance policy such a way that refuses to start a new process if it resources requirements might leads to the deadlock. So if any process it leads to the deadlock, we are not going to start the particular process right now. Okay, so start a new process, we have to define the condition in such a way that Pn plus 1, that is a new process supposed to be start, it has to satisfy the requirement, that is Rj, it falls in the category, then we have to stop it. Rj is greater than or equal to what I have claimed plus the allocated, the new available process, and it is already claimed, it's supposed to be greater than that. Okay, a process is only started if the maximum claim of all current processes plus those of the new processes can be met. So when the process supposed to be start, it has to claim all the maximum requirement, but this is the optimal way, but this leads to the worst condition right now. So the well-known example of the deadlock avoidance algorithm is called as a banker's algorithm. So with the help of this banker's algorithm, what we are going to say to the user is whether what is the state of the particular process, and we are going to define whether it is a safe state or whether it is in the unsafe state. Okay, so in the banker's algorithm we have a fixed number of processes and we have a fixed number of resources. A process, if a process want to start its execution, it may have a 0 or more resources already is allocated to it. The state of the system reflects the current allocation of the resource. Okay. Then we have two vectors we have already seen, resource which is defined by the R and available which is defined by the A, and we have two matrices, one is claim and another one is called as a allocation. Resource vector can be defined in V and allocation vector can be defined as resource vector can be defined as R and allocation vector can be defined as V, and two matrices, one is for a C and another one is for a A. Okay. Now we have to define the system in such a way that is what is the outcome of the banker's algorithm. The outcome of the banker's algorithm is allocate the resources for all the processes based on the relationships what we see in the earlier slides, and we have to identify whether the system is in a safe state or the unsafe state. Okay. What do you mean by safe state? The safe state, it means that at least one sequence of resource allocations to processes that does not result in a deadlock. Given a simple example of the safe state, we have four processes named as P1, P2, P3 and P4 respectively, and it requires some resources in such a way that R1 it needs X number, R2 it needs Y number and R3 it needs Z numbers. Okay. Now we will allow any one of the system, any one of the process P1, P2, P3 or P4, any one of the process allowed to execute, allocate all the resources. If after allocating it, it's supposed to complete its execution, it should not fall in the category of a deadlock state, and that is called as a safe state. If not, obviously that is called as an unsafe state. Now this is a typical diagrammatic representation that illustrates, that shows the safe state of the particular resource. See that I have four processes named as a P1, P2, P3 and P4. Now this is called as a claim matrix, and with respect to the process and resources, I have four processes and I have three resources. And allocation matrix, whatever may be I have claimed, as I said earlier, it may or may not be, the operating system will allocate less than or equal to the particular claimed one. Now this third matrix is the remaining resources available after the claim and after the allocation, what is the status. Okay. Now the resource vectors. Now R1 in total, in general, we have 9 R1 resources, we have 3 instances of R2 resources and we have 6 instances of R3 resources. So available is after the allocation for all the processes. Now the thing is, available vector is a 0. Why it is a 0 is because of available for R1 is 0 is because of all the resources are allocated. 6 plus 1 7, 7 plus 2 9, but it is already available is a 9 only. So the available is 0 right now. That is no R1 resources presently available because it is already allocated to the processes. Okay. And for R2 in available is 1, because why it is, for all the processes only the 2 resources of 2 instances of R2 is only allocated, likewise R3. Now this is on the initial state. Okay. This is on the initial state. So the total amount of resources of R1, R2, R3 are 9, 3 and 6 respectively. Okay. Now we have to allow the system to process, because we have allocated the resources, then we have to identify whether the system is in the deadlock safe state or not. Assume that, go to the figure BE. Now see in the process P1. Process P1 we need 3 resources of 3 instances of R1, but we have only a 1 instance of R1. So it is not possible to do it right now. It have to wait for another 2 more resources, 2 instances of R1. Let's take an example of a P2. P2 request is R1. As a request is 6 instances of R1 it is allocated, yes, exactly, and 1 instance of R2, yes, it is already allocated exactly, and the 3 instances of R3, but we have allocated only the 2 instances of R3, but in available vector we have a 1 instance. Assume that if we allocate that resources into the P2, whether P2 can able to complete its execution or not. Yeah, yes, if we are allocating is, obviously the P2 process will execute its completion of its operation. Now see that the allocation matrix, the claim matrix is everything is 0 because it's completed its execution. The allocation is also 0 and all the available resources are 6 instances of R1, and it is released by another 1 instance. Already 1 is there in R2, so totally 2, and we have 2 instances of R3 is already allocated to the process P2, available is 1, so all the 3 resources are deallocated from the particular process. Now at present the current status is 6 instances of R1 is available and 2 instances of R2 is available and 3 instances of R3 is available. Now we will check whether this is a safe state or not. We have to check whether is this a safe state or not. Yes, obviously the system is in the safe state, but we have to integrate with some additional questions also. That is, we need to identify the intermediate state of the particular process. Then only we can able to claim whether the system is in the safe or the unsafe. But it's in a very clear way. We can in overall perspectives we can say that we have allocated additional resources based on its claim. The process P2 is completed its execution without the deadlock state, so I am going to claim that now that system is in the safe state only. To integrate whether the system is in a safe state, we have to identify the further thing, that is called as, can any of the 4 processes be run to completion with the resources available? No, it is not possible. No, it is not possible. Still, to complete the resources, we need to allocate much more resources in that. So once if it is allocated, then only we can able to complete the execution for the process P2. It's not for the all the process. Okay. Can the difference between the maximum requirement and the current allocation for any processes be met with the available resources? What do you mean? Can the difference between the maximum requirement and current allocation for any processes met with the available resources? Yes, for the process P2 it is a met. That's why we have allocated 1 instances of R3 to the particular process to complete its execution. Okay, so now the system, it means that the system is in the safe state right now. Okay, that is in terms of the matrices and vectors introduced earlier, the condition to be met for the process I is Cij, that is the claim matrix minus the allocation matrix is less than or equal to B. That is what it will be. B is called as available. Yes, obviously the condition is met, so that's why I am going to claim that the system is called as a safe state right now. So these all are the corresponding explanations for the respective processes. How other processes can be executed without having any deadlock condition, without having any hassle-free resource allocation, how it will be completed its operation. If we do that, now we can say that the system is in the deadlock state only. Sorry. If we say that, we can easily define that the system is in the safe state only. That is, there is no deadlock in it. Now this is called as a banker's algorithm. Okay. When a process makes a request for a set of resources, we have to keep in mind of 3 things. One is called as, assume that the request is granted. Yeah, okay. After granting it, I need to update into the, that is the operating system supposed to update into the system status. These are the resources are allocated. Then we have to determine whether the system is in the safe state or not. If all these things is okay, then grant the request, or otherwise block the request because it leads to unavoidable consequences. Then the next figure it shows how to determine the unsafe state with the help of the same banker's algorithm. I will take an example of a process P2. Process P2, it's already 6 resources are requested and we have allocated the 5 resources. Yeah, okay. And it is also requesting another one additional resource because it is claimed is a 6. Yeah, okay. Then one additional unit of R3. Already R3 it requested is 3 but allocated is only 1. So the remaining instance is called as a R3 is there are the 2 instances are there. This is an initial vector. Okay. So during the execution it is asking another one resource. Okay. If we are allocating the another one resource to the process P2, then available resource for R1 is a 0. Yeah, okay. Already the 2 resources are allocated, one instances of R3 is already allocated to the process P2 and another one instance is also requested by the process P2. Yes, the 2 is available, so 1 we are going to allocate into the process. P1 requests 1 unit of R3 in parallel way because as per the deadlock condition, we don't want to go for the prevention mechanism, we want to execute the process concurrently. Assume that in the parallel way, if the process P1 in concurrently, if the process P1 is also making a request of some resources like R1, R2, R3, then we are not in the position to allocate those resources to the particular processes. Now this leads to the concept of the unsafe state. Okay, now are you clear about the safe state and unsafe state? Okay, thank you. Then what is the algorithm? What is the banker's algorithm to define all these things? Okay, it have the 3 data. It have defined the state which is called as structure which is called as a state. It defines what are the resources are there, what is the available, and what is the claim, and what is the allocation matrix. And after that, it will execute the resource allocation algorithm in such a way that the allocation of the particular process for any resources plus the request of the resource is greater than is a claim or not. Okay, already allocated and present request is greater than the claim or not. What is the purpose of the deadlock avoidance algorithm? Well in advance we have to define the process requirement, resource requirement. Okay, now see this condition, allocation already allocated plus the request is greater than the claim. Obviously we are not predicting the future request also, so it leads to the error. Okay, then if the request is greater than the available, yeah, if I am requesting, it is already allocated certain thing, if newly I am going to make the request, but the available, the request is less than the the request is greater than the particular available resources, obviously I am not going able to process anything, so I am going to suspend the process. Okay, if these 2 conditions are not met, then I am going to define the new state, that is called as I am going to allow the system to execute in it and to identify whether it is in the safe state or the unsafe state. So this is the way the resource allocation graph will be executed. Now this is the test and safety algorithm for the banker's algorithm, that is a test and as well as also the safety algorithm. Okay, so all the processes are there. Now while possible, find a PK in rest such that is what is the claim, and we will identify currently available. If it is a found, we can able to execute it, or otherwise it is means that it is a false. Okay, so the main advantage of this is it is not necessary to preempt and roll back processes as in deadlock detection. Okay, less restrictive than deadlock prevention. However, it does not have much restrictions on its use. 1. The maximum resource requirement for each process must be stated in advance. We have to do it well in advance. Next, the processes under consideration must be independent, that is, it should not synchronize with any other requirement while during the execution. There must be a fixed number of resources to allocate. No process may exit while holding the resources. Okay, any questions? I will repeat once again. So what do you mean by deadlock avoidance algorithm? The deadlock avoidance algorithm is the operating system has to define well in advance these all are the resources are required for the particular process to successful completion, point number 1. And point number 2, in the deadlock avoidance algorithm, we are majorly concentrating on the concurrency, not for the deadlock prevention mechanism. Okay, to handle the deadlock avoidance, we are having the Banker's algorithm. So in this Banker's algorithm, there are the two vertices and as well as also the two matrices are used. One is called as the resources that can be defined as R, and another one available resources that can be defined as V, and claim matrix that is defined as C of ij, and allocated matrix that is called as A of ij. Then we have to identify whether what is the state of the system, whether it will fall into the deadlock or not, and after that we need to define, we need to predict whether the system is in the or any process is in the safe state or the unsafe state while executing the Banker's algorithm. Thank you.